Alright guys, today we're going to talk about hypothesis testing. This is where it all comes together. This is what that's about. We're going to break this chapter up into 2 weeks though. It's a lot of material and it's a very important concept. We're going to be talking about hypothesis testing for proportion and mean. The two types, sigma known, sigma unknown, and this is exactly what we did for confidence intervals. So you should know when to use D and when to use T. Be sure you know what your symbols represent. If you don't know what your symbols represent, you won't be able to write down your information. If you can't do that, you can't do the work. So let's just informally look at hypothesis tests real quick. So ProCare Industries claim that couples using the pink packages of gender choice would have girls at a rate that is greater than 50%. Let's again consider the experiment where 100 couples used this packet and only 52 of them were girls. We're going to look at a formalization of this process later, but first let's just kind of write down what we know. First thing we always need to do is write down our claim. What are we claiming? These guys claimed that you'd have girls at a rate that is greater than 0.5. So the way we're going to write that is T is greater than 0.5. Notice that is P and not P hat. All right, so now we're going to write down what we know. 100 couples, so n's 100. And 52 were girls, so that makes P hat 52 out of 100. So that's all this really gives us. But we're going to use the normal approximation of the binomial to estimate the probability of greater than or equal to 52 to see whether or not this would likely happen by chance. To do that, we need to find mu. Remember, that's n times p. P is 0.5. Notice it's p, not p hat. So 100 times 0.5, well, that's 50. And sigma, well, that's square root of n times p times q. N's 100, p is 0.5, 1 minus 0.5 is also 0.5. So that's basically half of 100 and half of 50, so that's 25. Square root of 25 is 5. Or you can type the numbers in the calculator. Now we're using the normal approximation, guys, so we have to correct this 52 for continuity. So it's greater than or equal to, if you look back on that chart, that means we need to use 51.5 for our lower bound. And of course, infinity for our upper bound. That's what we're looking at. We're going to see how likely this is to happen with this mean standard deviation. So I'm going to grab the Casio. And I'm going to type it in mode inverse. No, we're going to do a normal CDF on this one. Lower bound is 51.5. Upper bound is infinity. This is all stuff you should already know how to do. Sigma, we calculated to be 5. And mu is 50. So we get a 38% chance of happening by chance. So since T is so large, we're going to be like, that's probably just happened by chance. It's not enough evidence to say, oh yeah, your packets work. So we're like, that probably happened by chance. So this is what hypothesis testing is for. It's to see whether or not someone's claim can be supported or not. All right, so what are the components of hypothesis tests? First and foremost, null and alternative hypotheses. We're going to be testing P and mu. This week we're only testing P, but next week we're testing mu. So this week all these mu's are going to be P's. Okay, so the null is H sub 0, that's pronounced H naught. It always contains the equality. and can be written in one of these three ways. Either mu equals a number, or p, mu is less than or equal to a number, or mu is greater than or equal to a number. Notice it has the equal to part in it. That's your null. The null has equality. The alternative, some books use H1, some use HA. I'm going to use H1. It does not contain equality. It can be written as not equal to, greater than, or less than. And the null and alternative are always the complements of one another. So if your alternative is not equal to, your null will be equal to. If your null is greater than or equal to, your alternative is going to be less than. They're always opposites. Some books will use equal to every time for the null. So like regardless of what the alternative says, it'll say equals for the null. I don't like that. We're going to go with, they're always the opposites, always complements. Our test statistics. You should again be familiar with these from last chapter. The test statistic for the proportion, here's the formula. That's what we're going to be dealing with this week. Next week we'll be dealing with test statistics for the mean, either Z or T, depending on what we're looking at. So Z is equal to P hat minus P over the square root of PQ over N. Notice this is PQ, not P hat, Q hat. Okay, a survey of 703 randomly selected workers showed that 61% of those respondents found their job through networking. Find the value of the test statistic for the claim that most, which is more than 50%, workers get their job through networking. Okay, so right now, we're looking for the test statistic. First thing you're going to do is write down your info. And I'm going to go ahead, highlight my claim, even though we don't need it for this one. Claim, most, that is more than 50%, get their jobs through networking. So the claim would be greater than 0.5. But for the test statistic, all we care about is the data up here. N is 703. P hat is 0.61. That means Q hat is 1 minus P hat, so 0.39. So now we've got the info we need in P hat and Q hat. Plug it in, that's your test statistic. P hat minus P, oh, we need P. P was more than 0.5, so that would be 0.5. So if we write down the hypotheses, this would be more than 50%, so that would be greater than 0.5. That would be P is greater than 0.5, and that would be our H1. That's got the greater than part in it. That means H naught would be less than or equal to 0.5. But this is the P. P is 0.5. Even if it's less than, greater than, less than or equal to, whatever, use that value for P. Okay, plug it in there. P times Q. Again, P is 0.5. That means Q would be 0.5. And if we plug all that in, whichever calculator you like, same old, same old. I'll use the TI because it's a little more complicated to type in. Numerator in parentheses. Denominator in parentheses. The numerator of the square root in parentheses. Denominator of the square root in parentheses. Close my square root. Close my denominator. I get 5.83. knowing what these test statistics are, these z-scores, if you remember back in the day, that 5.83 represents what? It represents how many standard deviations away from the mean we have. So that's way out there. If you remember, 2 standard deviations away was unusual. This is almost 6 standard deviations away. So that's definitely unusual. So this would say that, yeah, it's most likely that their claim is correct. The test statistic is way out there. And we'll again formalize this all at the end of the video. But for now, we're just going to look at it. And just looking at that 5.83, you should realize it's way out there. That's an unusual value. Now, specifically, it needs to be in the critical region. Our critical region is the set of values of the test statistic that cause us to reject the null hypothesis. So that's this right here. If we find our critical value, value right here, z 1.645, that'll be based on alpha, and we plot our 5.83, our test statistic, it's way out there. So that's definitely in the rejection region for the null. And again, our claim was here in the alternative. That was the claim. Since we rejected the null, we supported the claim, which was in the alternative. The significance level, that's still alpha, is the probability that the test statistic will fall in the critical region when the null hypothesis is actually true. So that's like our error, our possibility of making a mistake. So that's why we like to keep it really low. Excuse me. The critical value is any value that separates the critical region from the rest of the values that don't lead to rejection. So right here, that's the borderline. That's your critical value. That's your z. You'd use an inverse norm if it's a z. You'd use an inverse t or the charts for either one of those. And for proportions, we do use z scores. So if we just said, alpha was 0.05, then a z-score of 1.645 would be the critical value. It's like, okay, this is the limit. Anything past that, you reject the null. And I think 5.83 is definitely past 1.645, so we rejected the null. So, finding critical values. Use the significance level of alpha equals 0.05. We already did this last week for confidence intervals, but we always use the two-tail, if you remember. I told you we were going to talk about tails again. Last week we had a two-tail. It was, the left of the critical value and the right of the critical value because it was an interval. This time we might only have a one-tail, or we might have a two-tail still. So using the significance level of alpha equals 0.05, find the critical z values for each of these alternative hypotheses, assuming all the criteria are met. So P is not equal to 0.05. Not equal to would be the same as either being less than or being greater than. That's a two-tail. Anytime we have a not equal to, that's a two-tail. So we're going to, like we did before, have to split alpha in half for that one. And let's look at it. Alpha is 0.05. We got to split it in half. We're going to look up z of alpha over 2 because it's a two-tail. So if we use the chart, that would be alpha over 2 would be 0.025. So again, you should know how to find these on the chart, how to find them in the calculator, whichever one you're doing. 0.025 is our alpha. What we're going to look up for. Alpha 0.025 is coming down right here. That's negative 1.96. So this time we actually care about the negative and the positive. We have negative 1.96 and 1.96. It's a two-tail, so we're going to use both of them. For B, that's a less than. That's a left tail. Less than is left tail. Same alpha, but this time we're actually going to use 0.05. So we're going to look up the Z for alpha because it's the left tail. Since the left tail is going to be a negative number. Okay, so 0.05, if you look right here, that's negative 1.645. So negative 1.645. And that would be the left tail critical value. C is a right tail. So again, you can use the chart or the calculator. So let's see. If we go to inverse normal, 0.05, oops, that's sorting that wow, that's weird. 0.05, standard deviation is 1, meaning 0. Let me go back to mode 1. So it should clear all your data if you go back to mode 1. Area, that's your alpha value, 0.05. It's a one-tail test. This case is a right tail. Do not cut it in half. Keep standard deviation and mean the same. Because again, we're looking it up on the chart, we're getting that Z-score. You get 1.645. For the right tail, we get that 1.645. Right tails are always going to be positive. Left tails are negative. Two tails are both. And you got to cut alpha in half. TI, your inverse null program, second bars, number 3. So if we have the first one, that's the 1.96. If we have the other one, that would be 1.645. So again, that shouldn't be anything new to you. Let's see what those look like. So yes, curve sketching back. If we look at the part A, the not equal to, the two-tail, we got that 1.96 is the critical region. Below is negative 1.96, above is positive 1.96. So anything outside of that range will cause us to reject the null. On this one, it's a null. It's a left tail, so anything less than negative 1.645 would cause us to reject the null. This is the right tail. And it's called tails because the curve looks like it has tails on either side, I guess. Now, there is a p-value test. It's slightly different than the hypothesis testing. Some people like doing it better. It's just a different process. It doesn't matter really to me which one you do. I think you will have to do both on your final. So we're going to talk about p-value, but we're going to do that next time. For now, this video, we're sticking with the traditional method, looking at the critical values and the test statistics. So, our decisions based on our test statistic and critical region is either going to reject the null or going to fail to reject the null. That's our options. That's it. So again, we're going to look at the traditional method. We reject the null if the test statistic falls within the critical region. So if our test statistic is in this red area, we reject the null. Notice I didn't say anything about the claim. I didn't say anything about the alternative. I said the null. The claim could be either in the null or the alternative, so you got to watch where that is. And the p-value reject p if it's less than or equal to alpha. And here is how to calculate the p-value. I'm going to come back to this on the next video. For now, if you really want to, you can just pause it here and look at it. I'm not going over it today. After we decide whether or not we reject the null, we have to write our claim, or write our conclusion. So first, we write down our null alternative and say the claim is in the whichever one it's in. Then we find the test statistic, find the critical region, and see if we reject or fail to reject the null. Notice neither one of those says support. If we don't support the null, we either reject it or we fail to reject it. That's our option. Then we write down our conclusion based on where the claim is and whether or not we reject the null. So these are our four options. One of these is what you're going to be writing down every time. And the ... you know, that would just represent you copy down the words that the claim says. Claim that Doritos make you fat, whatever the claim may be. So if the claim is in the null and reject the null, we say there is enough evidence to reject the claim that whatever the claim was. So this is the only time we actually reject the claim. If the claim is in the null and we fail to reject the null, there's not enough evidence to reject the claim that whatever the claim is. Now, if the claim is in the alternative and we reject the null, then there is enough evidence to support the claim that whatever the claim is. Notice for the alternative, we use support. For the null, we either reject or fail to reject. The last case, the claim is in the alternative and we fail to reject the null. That would say there is not enough evidence to support the claim that whatever it may be. So here's the only time we actually support the claim. This is the only time we actually reject the claim. And here's a flow chart for those of you that are more visual. I don't know if you like it or not. It's the same thing I just went over. So you can pause it there and read it. It says identify where the claim is. Is it, do you reject the null? Do you not reject the null? Yes, no, right here. Now, let's get an example. Suppose a reporter claims that more than 50% of workers find their jobs through networking. This claim of P greater than 0.5 becomes the alternative hypothesis, while the null hypothesis would be P is less than or equal to 0.5. Further, suppose the claim that the sample evidence causes us to reject the null of P equals 0.5. So we're going to state the conclusion here. So it tells us we rejected the null. And the claim is that more than 50%. That doesn't have equality in it, so that is the alternative. So write down our ho and our how, H naught HA, or H naught H1, however you want to write them. So that is acceptable, but, you know, with my letters, it's safer for me to just use the 1, if you don't get confused with my O. Our H naught, the claim is, well, it's P is greater than 0.5, so that'd be H1. The claim. P is less than or equal to 0.5 is the opposite of that. And we rejected the null. Since we rejected the null and the claim is in the alternative, we can say there is enough evidence to support the claim that, what do they claim? Most workers find their jobs statement. Put a capital T. So if we look back at the chart on the previous page, we rejected the null, the claim is in the alternative. There is enough evidence to support the claim that. There is enough evidence to support the claim that, what was our claim? Most workers find their jobs through networking. That's it. That's how we write our answer. Now let's talk about actually testing a claim, a hypothesis test, starting with the proportion P. We're going to do p-test today. Not that kind, Trevor. The sample observations are simple random sample. Okay? You know, this is the same requirements to use the p-interval because we're approximating the binomial with a normal. Excuse me. So binomial conditions are satisfied, and n times p is greater than 5, n times q is greater than 5. Okay, let's look at it. Some notation. N is your sample size. You should know this. P hat is x over n. You should know that as well. All of this is from the same variables from last time. P, notice P, not P hat, is the population proportion. That's the population. P hat is the sample. We use the population in the null hypothesis. And Q is 1 minus P. And if we use the Q hat, it would be 1 minus P hat. The test statistic we're going to hire is P and Q, though. So again, this is the formula for the test statistic. We did that earlier. And to get our critical values, we're going to use the standard normal distribution chart or inverse normal, your choice. Let's actually try a hypothesis test. Okay. First thing, let's read our problem. Among 703 randomly selected workers, 61% got their jobs through networking. Use the sample data with a 5% significance level to test the claim that most workers get their jobs through networking. So that's my claim. Okay, so H1 and HO, let's see what we got. First thing, you know, I'm going to put HO on top. I like HO on top better. First thing we're going to do is write down our hypotheses, the null and the alternative. So the claim is that more than 50%. That's an alternative. It doesn't have equality in it. P is greater than 0.5. The null is the opposite of that. P is less than or equal to 0.5. The claim is in the alternative. The claim is that more than 50%, not greater than or equal to 50%, but strictly greater than. This is the claim right here. Okay, we've got our claim, we've got our hypotheses. Now let's write down our data. N is 703. P hat is 0.61. Alpha is 0.05. It's a one-tailed test, so we don't need to worry about cutting it in half. P is 0.5. Q is 1 minus 0.5 or 0.5. So now we got all the stuff we need, hopefully. Let's look at our formula sheet. And here we are. There it is. On the second page right there. That's my test statistic. Let's figure it out. The formula. So my test statistic. I have to use a pen. P hat, 0.61. minus P, 0.5, over square root P times Q, 0.5 times 0.5 over N was 703. All right, I'm going to type that in and see what it gives me. Use Casio. Make sure mode 1, because, well, that's where you do your calculations at. 0.61 minus 0.5 over a square root of a fraction. 0.5 times 0.5, 703. 5. Oh yeah, we got that same number because we got to do this problem. 5.83. That's what we're going to use. Now, you might want to be safer and do 4 decimal places, 3-1. Just in case, you know, it rounds to the same place where your critical values are. The critical values are usually 2 decimal places, so if you go 4 out, you should be good to go. I don't think we'll have any that are that close, though. So that's my test statistic, done with this formula. Now I need my critical values. Let's see, a greater than, so it's a right tail. So the critical values, well, I'm going to use my calculator again. It's a right tail. That means we don't cut alpha in half. It's one tail. Don't cut it in half. Mode, oops, 1, 3. Mode down 3. Inverse null. 0.05. And again, don't change this. We're looking at this number on the chart, basically. We don't want to normalize it. Don't want to standardize it. We just want that actual value. And we get negative 1.645, which is the same as we got here, you know, from the chart. It is a right tail, though, so we're going to take the positive, 1.645. We've got our critical value. We've got our test statistic. Now we need to draw it. So draw your standard normal curve, something like that. It can suck like mine, or you can draw nice and neat, doesn't matter. We know right in the middle is 0. So that's 0. My critical value, I'll put it right here, 1.645. So this is my critical region here. And let's see where that test statistic lies. 5.8, is that to the left of 1.6 or to the right? It's to the right. So here is my test statistic, 5.8. And yeah, I'd say that's in the rejection region, definitely. So that means we reject the null. Write that down. Whenever you graph your test statistic and your critical value, write down whether or not you reject the null or fail to reject the null. So reject the null. We're ready to write our conclusion. Our claim was where? The alternative. So the claim was in the alternative. We rejected the null. Go back and look at that chart if you don't remember. There is enough evidence to support the claim that most workers get their jobs through networking. And that's it. We're done. Oh, hey, by the way, TI people? Yeah, your calculator does this too. We can go to tests, And we're going to do a one prop z test. Number 5. P naught. That's the P. That's this, 0.5. X, well, so we have to multiply P hat times N to find out what X is. 703 times 0.61. And N, it might give us an error here, by the way, is 703. And we want a right tail. Yep, okay. We're going to have to round. We have to round the X value. It doesn't like decimals because this is, remember, it's a binomial thing, so it should be a whole number. That's going to round to 429. Oops, I changed that. And it gives us our Z critical value, 5.85. It's a little different because of that rounding, but you can still get it from there. Now, it also gives us our p-value. Remember, there's another test called a p-value test, and if p-value is less than alpha, you reject the null. Well, this is a decimal followed by 8 zeros and a 2. Yes, that's less than alpha. So that's how you can use the calculator to test these things. It's the same process for the mean. So it gives you your test statistic here. And it'll be a little different depending on if you're using, the actual 61% or have to round it to get the mean. Mendel. Let's do another example and then we'll be done. When Gregor Mendel conducted his famous hybridization experiments with peas, one such experiment resulted in offspring consisting of 428 peas with green pods and 152 peas with yellow pods. According to Mendel's theory, a fourth of the offspring of peas should have yellow pods. Use a 0.05 significance level with a p-value method. Yeah, we're not. To test the claim that the proportion of peas with yellow pods is equal to 1/4. Okay, again, first thing, let's find out what it's claiming. Claim yellow pods is equal to a fourth. So the proportion equals a fourth. Well, that's a small. P equals 1/4. And that's my claim. That means H1 will be P not equal to 1/4. So this time, we have a two-tail test. Our tail always comes from the alternative. So it's either left tail, right tail, or two-tail based on what the alternative says. So now let's write down our info. N is, doesn't say, does it? You gotta add. Well, 428 were green and 152 were yellow. That makes 580 peas. Monks sure do have a lot of time on their hands. So P hat would then be this 428. Oh, wait, no, this 152 we're just talking about yellow people. 152 out of 580. Okay, that's P hat. Alpha, 0.05. So let's make ourselves a little note. Cut it in half. Because it's a two-tail. And P is 1/4. That makes Q 3/4. Okay. The first thing I'm going to do is find my test statistic. If you don't remember the formula, you can look it up on your formula sheet on the second page right here. I guess I'll take a picture of it. Oh, there you have one. There it is again. So our test statistic is equal to P hat, that's 152 out of 580, minus P over square root of P times Q over N. Makes them a square root symbol. All right, type it in. Again, I'm going to type it on the Casio because, well, PI, you can just run the test, the hypothesis test on the calculator, and I'll give it to you. So we got a fraction, and inside the fraction we got a fraction, 152 over 580, minus another fraction, 1/4, with a square root with a fraction, and put that over 580. 0.67, okay? And I'm going to go 4 decimal places just to be safe, 0.6712. All right. Now I need my critical value. Excuse me. Thank you. So my Z critical value. And actually, it's a two tails, so we have values. Again, let me grab the calculator. Mode 3, inverse normal. Alpha is 0.05, cut that in half, 0.025. Or, if you want to, you can do 0.05 divided by 2, if you're not comfortable dividing by 2 in your head. And leave those alone. 1.96. So we have a negative 1.96 and a positive 1.96. Sketch it. And something like that. Here's 0. So I have a two tail. I'll call this my first Z critical value, negative 1.96. Over here, I'll say this is 1.96. And my critical region, my rejection region will be outside of those. So over here and over here. Let's see where our test statistic lands. I'll put it in red. Oh, it's right there, 0.67. So that's right here-ish, 0.67. It is not in the critical region. That means we fail to reject the null. Now we can write down our actual conclusion. So, fail to reject the null. The claim was in the null. There is not enough evidence to reject the claim that the proportion of peas with a fourth, with yellow pods, with yellow pods is equal to 1/4. So if we look, it says, we failed to reject the null, claim within the null, there is not enough evidence to reject the claim that there's not enough evidence to reject the claim that the claim. So that's hypothesis testing, people. And I'll post the homework. Next video, we're going to look at the p-value test. Oh, let me go ahead and do that one again with the TI, just so you can see how to use it. Go to stats, test, number 5, 1 test. This time we don't have to round, so it should be the same thing for statistics. P was 1/4. You do 1/4 or you type 0.25, doesn't matter. X, this time we had 152 and was 580. And we want a 2-tail. This matters for our p-value. Again, we'll talk about that next time. Calculate it. Z was 0.6712. There it is. Same thing. And again, we got a p of 0.5, so that p-value is greater than alpha, so we don't reject the null. So again, we're going to talk about the p-value test next week. I like the p-value whenever I'm using the TI. I like the critical regions whenever I'm using, well, I'm not using the TI when I'm doing it by hand, because calculating the p-value by hand is a little tedious. Anyway, that's it for today.